Hi guys, welcome back. I'm gonna have to change that banner. We're not doing chemistry anymore. I'll change it to a physics banner as soon as I get a chance. Today we'll just be continuing. I'll just finish off that intro to light lesson and talk about, the fact that it travels very fast and in straight lines, and talk about shadows and eclipses. You're just going to be watching this lesson video, taking notes like you did the last time. And then, see, I posted the same homework as yesterday. Make sure you have read and understood section 11.1 and complete page 469, number 1 to 9, same as yesterday, okay? In case you forgot your textbook, I've got the chapter 11 posted, and I've got the PowerPoint posted as well, even though I'm doing this video. So let's bring up that PowerPoint again. This is where we left off, that slide on lasers. So let's go do this and do that, and we'll just continue on. So how does light travel? Well, light travels very fast. Again, I'm going to put that symbol C. That stands for the speed of light. It's 300 million meters per second, but I'm going to write that in scientific notation this time, which would be 3.0 times 10 to the power of 8 meters per second. All right, that would be a 3 with 8 zeros on it, 300 million meters per second. And that was discussed briefly yesterday. But also, it travels in a straight line, and that's called rectilinear propagation of light. All right, it travels in straight lines. Now, there are some special cases in the universe where it does not travel in straight lines, like near a supermassive star or a black hole. But for all intents and purposes on Earth, where we're going to be studying light, it travels in a straight line. Like I wrote on the last slide, it's 300 million meters per second. To give you some context, sound travels very, very fast as well. And sound only travels at about 300 meters per second. So that is 1 million times difference. 1 million. Is that really right? Man, that is. 1, 2, 3. 1, 2, 3. 4, 5, 6 times faster. When we see an event, we see the light almost instantly, no matter how far we are away from it. But the sound catches up to you later. Where do you notice that? Well, probably in a lightning storm, in a thunderstorm, is where you've noticed it most prominently, where you see a flash of lightning. But if it's a few kilometers away, or even if it's a kilometer away, you don't hear the thunder for a period of time. And actually, it's almost kind of like a second sort of thing, whereas the sound gets to you, it travels about a kilometer a second. That's rough, but it's about a kilometer per second. So if you see a flash of lightning and it takes 3 seconds to get to you, then that's about 3 kilometers away. Just like last time, pause this at any point so that you can write what you need to down. This is the third time I've gone over the speed of light, though, so I don't know that you need it 3 times in your notes, but just to give you some context, it's way, way faster than sound. So, yeah, examples lightning. After we see a lightning strike, it takes time to hear the thunder. And then, even with the sun, it's a little bit of an abstract example, but it takes the sun's light 8.5 minutes to reach the earth. How far is the sun from the earth? Well, it's really, really, really far. We can actually calculate it using an age old formula, speed. Well, it has the symbol V in physics, but I'll just write it out. Speed is equal to distance divided by time. If I rearrange that to solve for distance, it's going to be distance is equal to speed times time. So if we really want to do that, we got to go 300 million meters per second times not 8.5 minutes, but it has to be 8.5 minutes in seconds. So we'd have to multiply it by 60 seconds per minute. And since I don't have a calculator, well, I do. I have my phone, actually. I'm going to run the numbers on this. So here we go. Here we go. I might as well give it a shot here. Go to Utilities, Calculator. Here we go. 300 million, 1, 2, 3, 4, 5, 6, times 8.5 times 60 equals. Well, the answer is this. 1.5 times 10 to the 11 meters. Now, if you don't like meters, that would be the same as 1.5 times 10 to the 8 kilometers. So that's 1 5 and then 7 zeros kilometers. So it's very, very, very far away. Now, again, you can pause that if you want that. I'm not going to ask you to calculate that on your own ever. I'm just trying to tell you how far away the sun is. It's really far. So far that it takes that long for the sun's light to get to us. Also, I was going to say that so if the sun were to explode or just disappear, let's say unexpectedly, we wouldn't find out for 8.5 minutes because the light or anything that from the explosion or disappearance from the sun could not reach the Earth for 8.5 minutes. You may have heard of a light year before. The next closest star, other than the sun, so the sun's light only takes 8.5 minutes to get to us, which is actually pretty quick. The next closest star is 4.5 light years away, 4.5 light years. Now, what that means is that the light from that star, it's called Alpha Centauri, and it means that the light from Alpha Centauri takes 4.5 Earth years to get to us. So let's say hypothetically you happen to be on Alpha Centauri and we were looking at each other through telescopes and you were to wave at me to say, hi, you're on Alpha Centauri. When would I see that wave? 4.5 years later. If Alpha Centauri blew up right now, we would not know it. Nobody on Earth would know it for 4.5 years because it takes 4.5 years for the light to get to us. All right, so that was just a brief discussion on light's really fast. Also, a little tiny bit about space is really big. We know that light travels in a straight line due to the fact that we see shadows. And these shadows can be sharp or fuzzy. So if we have a light source and we have like a wall over here, we see a shadow that looks something like that. Where this would be our shadow. We see shadows with sharp edges. Is this one going to give me the lines? No. Sharp shadows are observed if the source is small and the object is large compared to the source, which is what we have in this place. We have a small candle and we have a large obstacle in its way. Now, I'm doing my best to freehand these because I can't put a ruler on my computer screen right now, but when you're doing these ray diagrams, maybe I'll just try and do a slightly better job for you here. So I'm going to say there's a wall right here. Wow, that was supposed to be a straight line. That's a wall. And then from this light source, that's supposed to be a straight line and another straight line. And we get a nice sharp edge shadow right there on the wall. And like I said, sharp shadows are observed if the source is small and the object is large compared to the source. Moving on. Again, pause it when you need to. This should all be a part of your notes. Now, in this case, we get fuzzy shadows if the source of light is large and the object is small compared to the source. I'm actually going to draw that one too. So again, let's put a wall here somewhere in behind. And from the candle, you're actually going to get two parts that go there. And I'm going to put an arrow and an arrow and an arrow and an arrow. And from the bottom, you're going to get the same thing, one going there and one going on the other side of it. So what you get is a dark spot in the middle, and then you get these kind of gray, I don't know if I want to say gray. I'm just going to say less dark. And same with over here, and less dark. Now, there are special words for the dark and the less dark spots, and that's what accounts for these fuzzy shadows. So you get these fuzzy edges in these less dark areas, okay? And now, if you need to pause, go back and see how I drew these lines, because it does look a little ugly when it's all together like that, then go right ahead and do that. The light's always traveling that way. Now, those diagrams that we just went over can also explain things like solar eclipse. Now, a solar eclipse is where the moon goes in front of the sun. So this is the moon, this is the earth, and this is the sun. But you probably would have guessed that anyways. So I'm going to make the light go from right to left, which would be even more challenging. And I need the space, so I'm actually going to erase this stuff about moon, sun. Maybe I'll just put S, and then M, and then E. And that shouldn't affect my diagram. So I'm going to try and freehand this, but it's probably going to, it's not going to fail, but it's probably not going to look great. Oh yeah, beautiful straight line there. So from the top and bottom of the sun, you can see that there's no beams of light from the sun that can reach this spot right here on the earth, this spot right here. All right. And that's the dark spot. It's just like in that last example, and I'm just going to put a little arrow here, and that is called the umbra, and that is the dark spot where no light can get to. But light from, let's say, the top of the sun can get over to here. And again, I should have arrows on these. You should always have arrows on your beams when you're doing a ray diagram. So right below, I get a less dark spot, which is called the penumbra. And the penumbra is that less dark area, that less dark, that fuzzy area. And also from the bottom of the sun, I'm going to get another beam that goes to there. Now, again, that line is supposed to be straight. When you're copying these diagrams, I would encourage you to use a ruler. Not encourage you, demand that you use a ruler. So in that spot is also a penumbra. I don't know if I have any tools that will allow me to do that. Laser pointer eraser, yeah, I don't, not on this program anyways. If I had been in class today, I would have given you a handout with this picture on it, and you guys could have just used a ruler to get these. So one thing that you'll have to know for your next test is just the different parts of a solar eclipse. So first of all, what is a solar eclipse? It's when the moon gets between the earth and the sun, and you'll have to recreate this diagram. Now, if you can't pause it, go back and see how I did each beam. Then make sure that's something that you ask about when I return. But for now, just do the best that you can, and I just have a little bit more to go over. A lunar eclipse is when the Earth gets between the moon and the sun, and it makes it so we cannot see the moon. So I'm again going to go sun. That's supposed to be a straight line again. That's supposed to be a straight line. So you can see the entire moon falls in that umbra. Yeah, this is the Earth. That's the moon. That's the sun. Now, there's still penumbras, but we don't really need to draw them and confuse the situation here, because if I drew those extra beams, you'd find that they're like here and here, there'd be a penumbra. There always is going to be one on the top and the bottom when you do that. So that's what a lunar eclipse is. So you'll be asked, basic questions, even multiple choice questions, the lunar eclipse versus a solar eclipse. And then I do have test questions. I definitely haven't even thought about making the test for this chapter 11. But I do have questions that have diagrams like this where you just fill them out. Now, I'd never have a question that just says draw a diagram for a lunar eclipse, but I would give you a question that had the sun, the earth, and the moon drawn, just like this whole slide was set up originally, and you guys have to draw the light beams in and show where the umbra and the penumbra are. Okay. When light strikes an object, it can do one of three things. One thing it can do is it can be reflected, it can be absorbed, and it can be transmitted. Don't worry about writing those down right now because we're going to go through each of them in a bit more detail, okay? And if the light's transmitted, then that means that it can be transparent, which means all of the light goes through. For example, actually, maybe we are just, let me just take a peek here. I thought I had more on each of these. I have a diagram on each of them. Okay. So reflected means they bounce off. So I take it back. You do have to write this. Absorbed means the energy turns to heat. Ooh. I'm gonna write that out a little nicer for you. So I'm gonna say bounce off turns to heat. So it doesn't go through it, and it doesn't bounce off of it. It doesn't disappear, but it's turned into a different form of energy. In this case, it's heat. Or it's transmitted, which means goes through. When we're talking about transmitting light, you have transparent materials like glass and water, which means the light all goes through easily and a clear image can be seen. You guys know these terms already. Go ahead and pause it if you need to. Translucent means that some of the light goes through, but you can't see a clear image. So, like frosted glass. I'm sure you can think of a few other things, but don't worry if you can't. And then opaque really shouldn't be a part of transmitted because opaque is like you and me, that no light passes through and nothing goes through it. Like, I don't know, what are we going to put? I'm just going to write you. Light does not pass through you. Um, so you are opaque. And then just to wrap this up, go ahead and pause it and write this down if you need to. The diagrams for transparent would be when light hits it, all of the light goes straight through. These are supposed to be straight lines. I'm just struggling. Translucent, the light does go through, but some of it bounces off. And opaque, it can reflect off or it can actually just be absorbed. But I'm going to do a reflection example where all the beams reflect off of it. Maybe in this first one here, I'll make one of the beams reflect off because you get some reflection and some transmitted when the thing is translucent. And you even get the beams to bend a little bit. So translucent, transparent, and opaque. Those are those diagrams. Um, and again, I know it's been pretty definition heavy on this, but you'll need to know the difference between those things. But you guys, I think, already do because we've used these terms before. We haven't talked about reflection and absorption, but we have, we have now. So, and we'll talk in more detail about reflection when I get back. So yeah, how does light travel? There you have it. I'm going to get out of this PowerPoint now. You guys can go to any point in this video if you fell behind for any reason. And once again, I'm just going to revisit what there is left to do. All I want you to do is make sure that you have read section 11.1 and have attempted questions number 1 to 9 on page 469. Now, there should be a physics teacher in for me today, so he should be able to answer your questions, but I'm just sitting around trying to get better. Right now, I can't really walk, but I do have a computer. So if you have any trouble or any questions about any of that stuff, just go ahead and email me and I'll respond to you as quickly as I can. All right. So good luck with that. And I'm going to stop the recording now and I should be back soon.